Hi. In this session, we will discuss more about analytic functions. In the previous sessions, we have discussed about differentiable functions, analytic functions, and CR equations. Okay, and you know that for a function to be differentiable, it should satisfy the CR equations. Okay, so what are CR equations? Basically, it is if a function f of z is of the form u plus iv, the CR equation says that ux is equal to vy and uy is equal to minus vx. Okay, so these are very important equations in complex analysis, and you will be using those equations extensively in this module itself. Okay, and I hope you understand what's the difference between the differentiable function and analytic function. Okay, the only difference is that you talk differentiable functions even at a single, we can talk of differentiable functions even at a single point, but actually analytic functions are differentiable functions over a larger area. That's it. Okay, so that means you cannot say a function, when you say that a function is analytic at a point z0, it means that it is differentiable at z0 and also it is differentiable at an interval around z0 also. Okay, so when you talk of analytic function, it is the same as differentiable function. Only thing is that your consideration of points is much bigger than that of the differentiable functions. Okay, you can't say that by being a differentiable at a single point a function is analytic. So in order to for a function to be analytic, it should be differentiable at all points around a small interval of that point. Okay, so essentially it is differentiability only difference is that you are taking a larger set. Okay, so that's the only idea that much is required for you. Okay, I hope it is clear. Okay, so for a function to be analytic or differentiable, the condition is just the same. It should satisfy the CR equations. Okay, that is the essential criteria for a function to be analyticity. Okay, but just by satisfying the CR equations, a function will not be analytic. Okay, some more extra conditions are required. Okay, so we are talking of the reverse process here. That is, if a function is differentiable or if a function is analytic, it will satisfy CR equations. That is the necessary condition, or that is a very important or necessary condition for a function to be differentiable. Okay, but just by satisfying CR equations, a function need not be differentiable or even analytic. Okay, so this concept we will be exploring in this session. Okay, so just by satisfying CR equations, we can't say whether a function is analytic or not. Okay, so we'll be doing some problems in which they will be satisfying the CR equations, but essentially they will not be differentiable. So we'll be checking some problems which have this property. Okay, so let us try some problems here. Okay, so let us look at this problem here. Okay, so let's look at this function. So a function is f of x y is equal to root x y is there. Okay, you have to show that this actually will satisfy the CR equations at the origin. At the origin z is equal to 0, but we'll show that it will not be differentiable. Okay, so my function f of z is actually u plus iv. It is said to be, it is given as root of modulus of xy. Only real part is there, so your u is equal to root of modulus of xy and your v is equal to 0. Okay, now we will check the whether this function will satisfy CR equations at the origin. Okay, so just by taking the ux, uy, vx, v, etc., we will check whether this function will satisfy the CR equations. Okay, now since this is not a good function, you cannot take derivative directly because there is a modulus sign coming inside. Okay, so directly we can't take derivative, so we will apply the derivative formula. Okay, so before we apply the derivative formula, I hope you know what do you mean derivative. You know that it is, you know that f dash of x is equal to limit, you have studied in the lower classes, h tends to 0, f of x plus h minus f of 0 by h. This is the there are many definitions of derivative. This is the basic definition of a derivative. Okay, now what happens if my x is at origin? If it is f dash of 0, it will become simply limit h tends to 0. My x is actually 0, so f of 0 plus h minus f of 0 by h, or simply it is limit h tends to 0, f of h minus f of 0 by h. Nothing new is here, I am just applying the definition. Okay, so in other words, I can also write this as limit x tends to 0, f of x minus f of 0 by x, where instead of h variable I am just replacing it by x variable. Okay, so f dash or origin could also be written as like this. Okay, so I'm just tweaking it so that I can apply the definition in a much more easier method. Okay, I hope this definition is clear. It is a straightforward computation from the definition of the derivative. Okay, so if you have understood this, can you tell me what is dou u by dou x at origin? Okay, I am going to extend this definition here. So I am going to take ux at origin here. Okay, at z is equal to 0. Okay, for that I'll write. So you know that u is actually a function of two variables ux, y. So when you take ux, you are keeping your y as constant. Okay, so only your x will be varying. So this definition I will be carrying over here. So it will be simply be ux0. Okay, sorry, it is actually ux0 minus u00 by x. Why is it so? Because your y is constant, it is not varying when you're taking you are taking the derivative, and you are considering the point 0 0 only. So your y is constant means your y should be lying at 0 0 itself. Okay, only your x is varying, so it is ux0 minus u00 by x. So it is actually limit x tends to 0 ux0 minus u00 by x. Okay, so how did we get this relation? It is coming from this one only. Okay, your f dash of 0 is, if it is a one variable case, it will be simply be fx minus f0 by x. Now if you are considering u, it will be simply ux minus u0 by x, but your ux is actually of two variables, that is why I put it as ux0 minus u of 0 by x. Okay, so if you can understand how to write that thing here, you can do all the problems coming in this session here. Okay, that means I will write it once again. Your ux at origin, okay, I am writing it as simply, it is limit x tends to 0 ux0 minus u of 0 by x. Okay, because only x is varying here and your y is a fixed one. Okay, so if you understood that, can you tell me what would be uy at 0 0? You are going to differentiate u with respect to y. In that case, your y is remaining, your x is remaining constant, only y is changing, so it will become u, x is remaining constant. So since you are talking of origin point, x should be like 0 itself. U of 0y minus u of 0 by y. Okay, so this is limit y tends to 0 u of 0y minus u of 0 by y. So this is the definition of Cauchy-Riemann equations at definition of the partial derivatives at origin. Okay, so if you have understood this definition, and now let us apply this definition, check whether this will satisfy Cauchy-Riemann equations. Okay, now what are the Cauchy-Riemann equations? The Cauchy-Riemann equations are actually ux is equal to vy. Let us check it. So vy, what is ux? Ux already we know, it is actually limit x tends to 0. Please write to yourself, only then you will understand. ux0 minus u of 0 by x. Now this is your u here. Your u is actually root of modulus xy, and your v is actually 0. So what is the value here? It will become limit x tends to 0. What is u of x0? You just put x as x and y as 0 here, so it will become root of x into 0, that is actually 0, minus what is u of 0 you put x as 0, y as 0, you will be getting it as 0 minus 0 by x, which is nothing but x. It's nothing but 0. Okay, and what is vy here? The function v is anywhere 0, so vy also will be 0, nothing there is to prove. So you have got that your ux is equal to vy, okay, which is actually 0. And similarly, what is your uy? Uy also, it will be simply be limit y tends to 0 u of 0y minus u of 0 by y here. Okay, and what is u of 0y? U of 0y is again out of modulus of xy, which is again 0 minus 0 by 0, so we will be getting it as 0 only. And your vx will also be 0. That means your uy is actually equal to vx, but I can also say it is minus vx because I want to show that CR equations are the same, and also both of them are equal to 0 both, so this is true. So uy is equal to minus of vx, which is actually equal to 0. So we have got that CR equations are also satisfied at the origin. Okay, I hope it is clear. Okay, so this is the calculations here, you can check it out. Okay, now we will show that the function is actually root of modulus of xy is not differentiable at the origin. Okay, so I'll try to find what is f dash of z. So f dash of also z, also we can give the same definition, which is nothing but limit z tends to 0 f of z minus f of 0 by z. So using the same idea concepts of as u of x, we can also give the definition like this at the origin. Okay, so f dash of 0 is actually limit z tends to 0 f of z minus f of 0 by z. Okay, so what is that? That is actually limit z tends to 0 root of modulus of xy by x plus iy. Okay, so it will be simply if x plus iy tends to 0. Okay, now let us try to find out those limits. Okay, now so I am going to reach 0. So you know that for a limit to exist, it should be unique. Okay, you have already studied that in the CR equations. It should be unique. So whichever way you approach a point, you should get the limiting value as the same only. So if I come to left side, right side, here also, the limiting value should be unique. Okay, even if I come through straight lines here, parabolas here, then also your limiting value should be 0. So for a complex limit, so in the real case, in the real limit case, when you start saying a function as a limit, it means that if you come to RHL and LHL, the limiting value would be same. But in the complex case, you have complex points, so there are infinitely many ways to approach a point. So for a limit to exist, through all these ways, the limiting value should be the same. Okay, so the same concept you will be using here. So here my point is actually z is equal to 0. So in order for this limit to exist, through whichever way my z becomes 0, this value should have the same value, same magnitude. Okay, so suppose I am coming through the line y is equal to 0. Okay, what will happen to my limit? So when I approach this limit through the line y is equal to 0, my limit will become 0, right? Because x into 0, x plus ii, so it will be simply become 0. Okay, so even if I approach through the line x is equal to 0 through the through the y axis, then also my limit would be 0. Okay, so through these two ways the limit is actually 0. Okay, so it may appear that the limit is to be 0. Okay, so what happens if I am going to this point through the line y is equal to x? What will happen? Okay, suppose I am going to 0 through the line y is equal to x. So what will happen to my limit? My limit will become limit x plus iy tends to 0. We'll change it into root of x modulus of x into x. Why? Because my y is taken to be x by x plus ix, or it is actually limit x tends to 0 root of modulus of x square by x plus ix. If I take x square outside, it will simply be root 1 by 2, or simply it is simply y 1 by 2. So not 1 by 2, it is actually 1 by 1 plus I. Okay, so it is actually 1 by 1 plus I. Why? I can take x square outside, so only 1 will be remaining here. Root 1 is actually 1. So it is actually x by x plus ix, and your x and x will get cancelled out. X and x plus ix would get cancelled out. So you will get getting the value as 1 plus I. Okay, 1 by 1 plus I. So you are seeing that when I approach through the x-axis or y-axis, I am getting limit value as 0. But when I am approaching through the line y is equal to x, my limit value is different. Okay, so that means the limit is not unique. So this quantity will not exist. Okay, and hence we will say that this f dash of z f dash of 0 does not exist. Okay, generally I can talk like this. If I want, if I take my path as simply y is equal to m, this is the general approach, and if I take the path as y is equal to mx, okay, instead of y is equal to x, it will cover all the paths in all linear paths, not all the paths, it will cover all the linear paths like y is equal to x, x is equal to 0, and everything is covered here. So if I take this path to reach 0, what will happen? My ratio will become, so if I take the path y is equal to mx, what will happen? My ratio of root modulus xy by x plus iy, it will become root of x into mx by x plus imx. So that is actually x into root of modulus of m by x into 1 plus im. So if you take the limit, what will happen? You will be getting the value simply root m modulus m by 1 plus im, which depends on m. Okay, so which depends on n means if m is 0, you will be getting 0. If m is 1, you will be getting 1 by 1 plus I. If m is 2, I will be getting different value. So the limiting value changes depending on the direction. That means limit is not unique, and hence the limit will not exist. Okay, so in that case also we will say that f dash of 0 does not exist. So we have now obtained a function which actually satisfies CR equations at origin but is not differentiable. Okay, so that means Cauchy-Riemann equations are not enough for a function to be analytic. Okay, so if a function is analytic, definitely it will satisfy Cauchy-Riemann equations, but merely Cauchy-Riemann equations are not enough for a function to be analytic. Some more extra conditions are required. So we'll say that Cauchy-Riemann equations are not sufficient for a function to be analytic. Okay, so I hope it is clear. So we'll do one more problem related to this. Okay, so let us look at this question also. Look at this question here. So let us try this question also. So in every problem you should know how to write that ratio here. Okay, so what is your ux? Your ux at 0, it will be basically 0 will basically be limit x tends to 0 u of x0 minus u of 0 0 by x. If you not write this one, every problem you can do it easily. Okay, so now if I look at this question here, what is my u? My u is the real part, so the part which does not contain I, so it will simply be x cube y raised to 5 by x raised to 4 plus y raised to 10. Okay, similarly, what is my v here? V is actually x square y raised to 6 by x raised to 4 plus y raised to 10. Okay, so what is my ux at origin? What is my ux at 0? It is actually limit z x tends to 0 u of x 0. What is u of x 0? U of x 0 is actually x cube into 0. Anyway, it will become 0 minus u of 0 0 is always 0. Okay. So here there's one more condition, z not equal to 0 and 0 when z is equal to 0, only then it will be true. So u of 0 0 is taken to be 0 here by x which is 0. Okay, similarly what is your vy? Vy also will be limit u v 0 y minus v 0 0 by y. If you know how to write it, it's very simple. So it will be simply become limit y tends to 0, v of 0 y is actually 0 minus 0 by y again 0. Okay, so by checking out all these relations would be satisfied, so we can say that the function is will satisfy the CR equations. Okay, now let us look at the derivative one. Okay, so it is actually you have to check out, what do you have to check out? You have to check out limit z tends to 0, right, x square y raised to 5 into x plus iy by x raised to 4 plus y raised to 10 into x plus iy. Okay, how did I get this? It is simply be, it is fz minus f of 0 by z. Okay, fz is this quantity, f of 0 is actually 0, by z is this, so you will be getting this quantity. Okay, so or in other words, you have to find limit x plus iy tends to 0, x square y raised to 5 by x raised to 4 plus y raised to 10. Okay, I'm just cancelling out this x plus iy and x plus iy. Okay, you should write with me, only then you will understand, otherwise you won't understand, because this is a very simple computational one, so only you have to write it with me, only then you will understand. Okay, so what can you say? Will this limit exist? So basically we are reaching the point z is equal to 0. If I come through the x-axis, my y is 0, you will be getting the limit value as 0. If I come through the y-axis, my x is 0, then also your limiting value will become 0. If you just put x is equal to 0, it will be 0. Okay. If I come through the line x is equal to y, what will happen? If I come through the line x is equal to y, it will become limit x tends to 0, x raised to 7, right? Because x is equal to y, x raised to 7 by x raised to 4 plus y x raised to 4 plus x raised to 10. So at max you can limit x tends to 0, it will become x cube by 1 plus x raised to 6. Okay, so when x tends to 0, also this will become 0. So even in the line y is equal to x also, this will be true. Okay, but the problem with complex analysis is that you can reach a point through infinite number of ways. It can be through straight lines, it can be through what you say parabolas, curves, anyway. So you can reach a point through infinite number of ways, and in all these infinite number of ways, it should satisfy the same, it should be the same value, only then limit would be exist. So merely by saying x is equal to 0, y is equal to 0 and everything, we can't conclude that this limit will exist. Okay, now the problem with this x, y is equal to x is that this x is not completely eliminated here. Okay, so can you completely eliminate this x and y from this expression, just like we did in the last problem? In the last problem, when you took x is equal to y, all your x got cancelled out. So you similarly like that, can you cancel out all these x factors by a proper substitution of y or x for that case? Can you do that? So if I take, so if you look at this one, suppose I want to make all the powers to be the same. Okay, so I want to make all the powers to be 10. So what will I do? Suppose if I take x is equal to y raised to 5, what will happen? My numerator would be limit x plus iy. Okay, so it will be simply be no, if I take not okay, if I take x square is equal to y raised to 5. Okay, that is x, I take x square is equal to y raised to 5, or simply x is equal to y raised to 5 by 2. What will happen? Okay, so in that case what will happen? Your numerator would be simply be y raised to 5 into y raised to 5, that is y raised to 10 by, again x square is y raised to 5, so so it will become y raised to 10 plus y raised to 10, nothing but y raised to 10 by 2 y raised to 10, which is 1 by 2. Okay, so if I go to z is equal to 0 through the point x square is equal to y raised to 5. How is this x square is equal to y raised to 5 obtained? It is not obtaining from thin air. It's very simple thing. I am trying to eliminate both x, y and y to get a fixed constant. Okay, so that for that I should make both the numerators to be the same, both terms to be the same. So what can I do? I can put my x square is equal to y raised to 5. So the denominator will become y raised to 10, y raised to 10. Here also I will be getting y raised to 10. So from there only I am getting the substitution. That's it. Okay. I can also put mx square is equal to y raised to 5. So in that case, my limit will depend upon m. Okay. So here x square is equal to y raised to 5 is obtained by trying to eliminate this x and y. That's it. Okay. So if you do like that, what will happen? Your numerator will become y raised to 5, y raised to 5, y raised to 10, y raised to 10. So it will simply become 1 by 2. Okay, so now we have got that. When I go through the x-axis, I am getting limit as 0, but through this path, I am getting the values y is equal to 1 by 2. So it is differing. So the derivative will not exist. So that means Cauchy-Riemann equations are satisfied, but derivative will not exist. Okay. Similarly, you can look at this problem here. Okay, that is x cube into 1 plus I minus y cube into 1 minus I here also. That also you can try. So Cauchy-Riemann equations you can easily try it out, no issue. But otherwise also you have to check it out. Okay, so please try to do this as a homework by doing some suitable modifications here. Please try to do this as a homework also, and try to check whether this will be differentiable, at z is equal to 0. Okay, so I hope it is clear. So only thing which is required for you is that you should know how to write this ux at origin. Okay, that is actually limit x tends to 0 ux minus u of 0 by x, u of xy minus u of 0 by x. Okay, that is clear. Okay. Now, if the Cauchy-Riemann equations are not enough, what more extra conditions is required for you? Okay, so that is next one. So, if a function is set to be analytic at a point, if it is a function is should be analytic if it will satisfy the Cauchy-Riemann equations plus the partial derivatives must be continuous. These are the two conditions. That is, one is first of all your partial derivatives ux, uy, vx, vy, which are in the Cauchy-Riemann equations, it should be continuous for one condition. Second condition is that your Cauchy-Riemann equations should be satisfied. That is, ux is equal to vy and uy is equal to minus vx. So this should happen. Okay. So if these two conditions are satisfied, we will say that the function is analytic. Okay, so the proof of this is not required for you. Only remember these conditions. It's very simple. So just you have to check the Cauchy-Riemann equations and also you have to check whether the functions are continuous. Okay, there is nothing to check because usually you should have an idea of continuous functions. So which all functions are continuous? All polynomial functions are continuous. Okay, all polynomial functions are continuous, like x square or z square plus z square plus 1. All polynomial functions are continuous and differentiable. Okay, all rational functions are continuous and differentiable except at points where denominator is 0. Okay, for example, z square plus 1 by z minus 2 is 2 is actually continuous except at z is equal to 2 because the function is not defined there. Okay, and similarly e raised to z is continuous, log z is continuous wherever defined. Similar sin z, cos z is continuous everywhere, tan z. Okay, a trigonometric function tan z, cot z, sec z, cosec z are all continuous at all points wherever defined. Okay, so tan z is not defined at z is equal to pi by 2, so there it is not continuous. Okay, so these functions are continuous wherever they are defined, and their combinations also will be continuous. For example, e raised to z into sin z are continuous, z into e raised to z are continuous. So usually you will only get these type of problems. Okay, you will have polynomials, you will have rational functions, you will have trigonometric functions, exponential functions, and their combinations. Only this will be there for your examination. So all of them will be continuous. So you will have to check it out where the function is not defined or not. Okay, so let's now do some problems here. Okay, and one more thing I have to tell you is that you should know the relation of derivative of function. That is, what do we mean by f dash of z? F dash of z is nothing but ux plus I vx. This is obtained from the derivation of Cauchy-Riemann equations. Okay, this is obtained from the derivation of Cauchy-Riemann equations. So since we know Cauchy-Riemann equations, we can also write down some other relations connecting this f dash of z. I can write f dash of z is equal to, since ux is equal to vy, I can write vy, and your I vx is equal to minus uy, I can write this minus I into uy. Okay, so this is also true. Okay, or I can write simply in terms of v only. Okay, your vx is equal to vy, so it is vy plus I vx. Okay, similarly, your you can also write in terms of u only, that is simply by ux minus iui. So many relations are there. Any one you have to study, any one, rest everything you can derive using the CR equations itself. Okay, so try to study any one only. Okay, so this is there. Now let us try to do some problems here, okay, of checking whether a function is analytic or not using CR equations and the extra condition here, that is continuity. Okay, so look at this function f of z is equal to z. So what is your u and v? Your u, f of z is actually z, so your that is actually is equal to x plus iy. So your u is x and v is y. Okay, so what is your ux? Ux is 1, uy is 0, vx is 1, vy is equal to 0. Okay, so remember here, first in the first step, check the CR equations. Check the CR equations. What are CR equations? Ux is equal, sorry, vy is 1 here. Ux is equal to 1, vy is equal to 1. So ux is equal to vy and uy and vx is equal to 0 here. Okay, so uy is equal to minus vx and both of them are 0. Okay, so CR equations are satisfied. Okay, from this you cannot say the function is analytic or not. Next, what you cannot say whether the function is analytic or not. You have to write one more condition. You can say that you can see that these are all simple constant functions. So you can directly say that since ux, uy, vx, vy are constants, they are continuous. Okay, so this step should be there, only then you will be getting mark. Okay, so this step you should mention here. Here since ux, uy, vx and va are constants, they are continuous, and therefore since the function satisfies CR equations and are continuous, it is analytic everywhere. Okay, it is analytic everywhere because there is no point of discontinuity here. It is analytic everywhere. Okay, it is analytic everywhere. Okay, now can you find the derivative of this? What is your derivative? Your derivative is actually ux plus ivx. Okay, so what is your u here? U is x here. What is ux? Ux is 1. What is vx? Vx is 0. So derivative simply be 1 only. Okay, I hope it is clear. Okay, now let us check one more function. F of z is equal to e raised to z. Okay, so what is the function? E raised to z. What is the real part? Real part is actually e raised to x plus iy. That is e raised to x into e raised to iy. Okay, that is e raised to x into cos y plus I sin y. So what is your real part? Your real part is e raised to x into cos pi and v is equal to e raised to x into sin y. Okay, now we can see that straight away that what is your ux? Your ux is actually u raised to x into cos y itself. What is your uy? Uy is minus e raised to x into sin y. What is your vx? Vx is e raised to x into sin y. What is vy? Vy is e raised to x into cos y. Okay, now you can check whether ux is equal to vy here. Okay, so because ex is equal to vy, so e raised to x into cos y, e raised to x into cos y, and similarly uy is equal to minus vx. So CR equations are satisfied. Okay, now there's no problem anywhere in the plane. Okay, and similarly these are all trigonometric and exponential functions and their combinations. So sin x is continuous, e raised to x is continuous, no issue is there. So you can straight away say that since these functions are combinations of trigonometric and sine and e raised to x which are continuous and differentiable everywhere, ux, uy, vx, vy are also continuous. So that step also you should write. Okay, so since ux and ex and sine and cos are continuous everywhere, you can say that ux, uy, vx, vy are also continuous. Just write the statement. There is no need to prove anything. Just write this small statement. Okay, therefore the function is continuous. Okay, this is how you should write the problems in the examination. Okay, now can you find f dash of z? Now f dash of z is actually ux plus ivx. What is ux? Your ux is e raised to x cos y plus what is your I? Your I vx is e raised to x sin y. Okay, so that is actually e raised to x into cos y plus I sin y. Now that is cos y plus I sin y is iy itself. So e raised to x into e raised to y, that is nothing but e raised to z itself. Okay, so you have got the derivative of e raised to z is e raised to z itself. Okay, similarly you can check for sin z also. Okay, so how will you check it out? So first you find u and v. What is sin z? Sin z that is sin x plus iy. Applying the sum rule, it is sin x cos iy plus cos x sin iy. Okay, and sin iy here, and you should remember some basic properties here, that is cos ix is equal to cos hx, and similarly sin ix is equal to I sine hx. Derivation is not required here. You can just coming from the definition of hyperbolic functions itself. Hyperbolic functions is actually, you know that cos hx is e raised to x plus e raised to minus x by 2 here, and sin hx is e raised to minus x plus e raised to minus x by 2, and if you substitute ix for this x, you will be getting these relations. You can check it out. If you want, you can try it out. This is, but you have to remember this relation. If you know this relation, you can find u and v here, because from here I can't say what is u and v, because it should be of the form some I should be outside here, but I is actually happening inside the sign only, so I can't straight away say what is u, what is v here. Okay, so what will happen here? So my sin z will be actually sin x, and cos iy is cos hy plus cos x, and sin iy is I sin hy. Okay, so only if you use this relation can I separate out what is u and v, because otherwise my a is lying inside this sign, so from that I cannot say what is u and v, because I should be lying as a separate entity here. So for that I am making use of this relation. Okay, from this you will be getting my u is equal to sin x cos hy, and my v is equal to cos x cos hy, and you check what is ux, what is uy, vx, vy, and also make use of the result that it is cos x sin hy. Okay, so please correct it. Okay, and you have to make use of the results of derivatives of hyperbolic functions. Derivative of cos hy is sin hy, and derivative of sin hy is basically cos hy only, nothing new is there. No negative sign is there, so just make use of that results to find ux, uy, vx and vy, and just write down that since these are continuous everywhere, the function is also continuous, and hence it is analytic, so it should come there. Okay, if you want, I'll just write it down here for you. What is ux? Ux is nothing but cos x cos hy, vx is nothing but so uy is nothing but again sin x, derivative of cos hy is sin hy, and what is vx? Vx is actually minus sin x sin hy, and what is vy? Vy is nothing but cos x again cos hy. Okay, so from this you will be getting that. Okay, nothing new is there, and also try to find the derivative here and tell me what's the derivative. Okay, so moving forward, now let us look at some important functions called log z. Okay, so log is not, it is not very easy to find u and v, because if I take it as log of u x plus iy, I can't separate it out easily in this form. Okay, for that what I will do is that I'll try to take I outside. For that I'll convert the sum into a product, because I know the relation log ab is equal to log a plus log b. Okay, so in order to use that result, I'll make a product here. So you know that x plus iy can also be written as r e raised to I theta in the polar form. You studied polar form in your lower classes. So what is your r here? Your r is actually root of x square plus y square, and what is your theta? Theta is equal to tan inverse y by x. So if you use that result, what will happen? Your log z is actually log r e raised to I theta. Okay, so it is r into log r plus log e raised to I theta. You know that log e is 1, so it is actually log r plus I theta. Okay, so your u is actually log r and v is equal to theta. Okay, in the terms of x and y, if you want, it will be log root of x square plus y square, or simply u is actually 1 by 2 log x square plus y square, and your v will be actually tan inverse y by x. Okay, and you can see that this function is not defined at x is equal to 0, so this will not be the log z will not be differentiable at z is equal to 0, but because it is not defined at the function, and if you define the value x is equal to 0. Okay, now if you want, you can check ux and uy, vx and vy. Since except x is equal to 0 at every point, this is basically simple functions only, so you can easily find out ux. So what is ux? Your ux is actually 1 by 2 into 1 by x square plus y square into 2x, or simply it is x by x square plus y square. Okay, you can see that it's not defined for x is equal to 0, so xy is equal to 0, so it is not analytic at x is equal to 0. Okay, and what is uy? Uy is again 1 by 2 1 by x square plus y square into 2y, so it is actually y by x square plus y square. Okay, and what is your vy and vx? Please check it out that also. Vx is actually 1 by 1 plus y by x the whole square, and derivative of y by x with respect to x is minus y by x square. Okay, and simplify it, so it will be getting minus y by x square plus y square. Okay, similarly if you take vy also, you will be getting this as 1 by 1 plus y by x the whole square into 1 by x. So when you simplify, I think you will be getting it as x by x square plus y square. Okay, from there also you can write it out. Okay, now if you want, you can write, so you can say that the function, these are actually polynomials only. Polynomials, I told you, it's rational functions only. Rational functions, I told you that they are everywhere continuous except at points where they are not defined, but you can see that it is continuous everywhere except at x, y both equal to 0. So except at z is equal to 0, the function is analytic. Okay, so that is the only point of discontinuity. Okay, and similarly if you want, you can find out the derivative also. Derivative is actually ux plus I vx. So please write down what is ux. Ux is actually, what is your ux here? So I think we have written here. So okay, so your u was 1 by 2 log x square plus y square, and your v was tan inverse y by x. So derivative is actually ux plus I vx. What is ux? Ux is actually 1 by 2 into 1 by x square plus y square into 2x. So it is x by x square plus y square. And what is your vy? Vx is actually 1 by 1 plus 1 y by x the whole square into minus y by x square. So it is minus y by 1 x square plus y square. So ux plus I vx is your derivative. So it is x by x square plus y square minus I into y by x square plus y square. So it is x minus iy by x square plus y square, or it is actually z bar by x square plus y square. Now x square plus y square I can write as its modulus actually. So it is z bar is equal modulus of z square, and you know what do you mean by modulus of z square? It is nothing but z bar. So it is z bar by z bar. So we'll be getting it as 1 by z. Okay, so derivative of log z is actually 1 by z except that z is equal to 0. Okay, so that's it. You can try to do this problem also. It's basically, it will be analytic everywhere except at the point where z is equal to minus 1. Okay, because the denominator will not be 0. Okay, and also please try to find out what is u v by separating it out and try to do it. So please try to do that also, or you can use other methods also here. Okay, so that's it. Okay, thank you.